the open source neuromorphic hype train, right? So the idea is that where we've seen deep learning, we've seen the hype train of deep learning kind of be enabled because of open sourcing, amongst a few other things, the proliferation of sensors and all the stuff that you see in the first two paragraphs of basically every research paper. But what I'm aiming for and what I'm getting involved with is porting some of those ideas and principles to hardware. We've seen Google throw a lot of money at a couple of foundries to enable open sourcing process design kits, et cetera. And that pretty much lets us do a lot of high risk, really interesting chips that we otherwise might not be able to justify porting. So with that being said, this is my actual title slide with Thomas speeding towards some future neuromorphic fancy chips. But yeah, so we've seen a bit of a trend with chips across various levels of abstractions from process technology, right? Going from controlling one single dimension when we apply voltage and track electrons on a dimension, and then we go to FinFETs where we can control 2 dimensions and then gate-all-around FETs. And we've seen the same kind of thing go in memory circuits where we start taking advantage of the 3rd dimension, vertical real estate. Likewise, AMD's 3D vertical cache slapped a bit of SRAM on top of your microprocessor. So the point is we're seeing vertical integration all across the board, image sensors and processors as well with dynamic vision sensors, and prophecies, cameras, and any. What comes next? Once we exhaust all 3 physical dimensions available to us, how can we keep moving forward? I'm preaching to the choir here, but the 4th dimension makes sense. Why not learn how to extract something interesting from time, right? Let's use spikes. Let's distribute some of our learnings in time. So obviously there's going to be a bit of a cross-stack approach where we try to address algorithms and hardware concurrently. So yeah, we take the computational principles that underpin the brain and integrate them with silicon. I said that really fast because you've heard that to death. A couple of ways to approach this: bottom up, in-memory compute, data flow; top down, focusing on the algorithms, tiny ML, compressed models, and all of that. And of course, the brain, I like the way I view it, is that it sits in this kind of nice little niche in the middle there, where spike-based processing and temporal coding kind of gives us an excuse to go both top down and bottom up. And that's a lot of fun. Let's see if I can kind of fly through this. So yeah, once again, thank you, Gerd. Let's see if we can play that video. I'm not sure if I have the capacity to do that myself here. But yeah, on the far left is just an example of a material stack. Kind of give a high-level overview of how I landed in neuromorphic engineering and then how that subsequently led to open source hardware. But the idea is that, is there any chance we could play that video on the left there? So yep, awesome. You apply a voltage to a material stack, memristor, resistive RAM, whatever you want. And you're basically modulating a conductive ion pathway in order to modulate the resistance. And the nice thing is, because we're often operating with nanoscale thin films, the voltage you need to apply is often very small to build up a very large electric field. And if you remove that voltage, you get a non-volatile memory. Your conductance pathway stays the way it is. We can kind of scale this up. It's fabricated in the back end of the line. We use a mix of KCl, KVL in order to parallelize a sum of products, a matrix vector multiplication. And that maps very simply to a lot of the operations that we like to see in deep learning. So that's all well and good. So the first very painful chip that I worked on that used the integrated RAM in the back end of the line, not going to go into the nuances, but the idea was we had this ADC, a sigma delta modulator, and basically using time to extract a bit more precision, right? If you read out for a longer duration, then you get a more precise output and a more precise current readout, charge readout. So that's great. There are a lot of cases with neural nets where you can approximate things. There's cases where, if your activation is super high, don't worry about precision. We're happy with the fact that it's high. If your, pre-ReLU activation is low, well, it's going to be 0. So we don't really care if we clip it, if we lose a bit of precision. So that was the incentive to go there. Now, I'm not really interested in numbers at the moment, but the challenges that we faced, this is in my view, kind of non-neuromorphic. This is just conventional deep learning here. But the challenges were that, yeah, the benefits that this chip saw, maybe it's the fact that I was a crappy designer at the time, were that these improvements were kind of insufficient to justify potential startup costs of integrating slightly exotic materials into your process tech. Alternatives, yeah, scaling, there's a lot of scaling challenges when it comes to this analog mixed signal type of computer. Of course, microprocessors and modern technologies are not tailored towards analog blocks. And in this case, at least, ADCs very much dominated latency and the power overhead. It was a very significant chunk of this core. Of course, the things that are going to dominate that will change once you scale up and you have chip-to-chip communication. But where we ended up with was how can we amortize, or how can we reduce our dependence on ADCs, on analog, on data converters? Well, spikes, ones and zeros. So can we somehow exploit that? Can we get the best of both worlds, where we have in-memory compute with RRAM, while still and sidestep some of the challenges that come with that, sidestep some of the variations, all of the issues that come there, and throw in a few spikes, right? So let's see if, right. What that led to was building a Python library. At the time, I had no idea how to train a spiking neural network, least of all how to code in Python. So this was a fun little exercise to learn both of those things. So we developed SNN Torch. There's a few other libraries out there. I can see you in there. And so it's all open source. That's all well and good. And the goal was to train spiking neural nets that we could compile onto our chips, right? So there's a few features for online learning in a fairly rudimentary fashion. Integration with PyTorch is a fair few of those other libraries out there. Do shout out to Norse here. They're accelerated on CUDA thanks to, I guess, we're just piggybacking off PyTorch's advances here. We also worked a little bit with GraphCore to make them, I guess, compilable for intelligence processing units as well. But also, yeah, the way that people are doing these things means that they're lightweight enough for CPUs as well. And a few places have been using it, which is cool. More importantly, this library is very rigorously documented with a series of pretty nice tutorials. I think most of the people in here probably don't need them, but it has kind of become an entry point for a lot of students to learning how to use SNNs in a way that's functional, I guess, in a way that shows how you might be able to compete with the deep learning crowd, algorithmically at least. So yeah, I strongly recommend checking those out. A very ground up approach to learning how to do this and kind of lowering the barrier to access some of this highly interdisciplinary information that people that aren't kind of embedded in groups that historically do neuromorphic research might not necessarily have access to. And there are a lot of those groups. In the course of doing this kind of link between backprop and STDP emerged, where, of course, STDP, where we like it because it's a local learning rule. We hate it because we don't really account for anything other than a pair of neurons. So you're kind of snipping away the rest of the brain. So, I mean, how reliable is it? And it's reliable enough to solve MNIST. And as we all know, MNIST is a very representative data set of what the real world looks like. I told myself I wouldn't be sarcastic during this presentation. It's like one strike against me. So of course, if we apply backprop through time in the classical surrogate gradient descent, it's classical now. But yeah, as you move backward in time through something that leaks, right, then the gradient of a signal that occurs at, say, t equals 0 is going to exponentially decay as you move forward in time, right? And so that's kind of represented here. Say on the far right, we have t equals 0, and as we go backwards in time to, say, t equals -5, then you've got this decay, this leakage term that keeps on scaling your gradient exponentially. So your gradient gets smaller and smaller as you move back in time. And then you apply that gradient as a weight update, right? In a similar fashion, STDP exponentially decays as the distance between the spike of a parent, or each spike of a presynaptic and postsynaptic neuron increases as well. So that was kind of a curious link that we decided to play with. So I'm talking about things that are still very much a work in progress, right? But at the moment with SNN Torch, we have got a branch somewhere out there that's, I keep saying I'll merge it in 2 weeks, and then I keep finding these errors and bugs as you do. But yeah, we're taking this leaky integrate and fire neuron, having a STDP specific neuron there, that will let you kind of do globally modulated STDP and take it a step further and do something a little bit more guided in the spirit of what I think Adam was talking about yesterday, where you can use rejection sampling. So if your STDP update doesn't do a good job, forget about it, right? So hopefully making local learning rules a little bit more practical. By sitting on top of PyTorch, that also lets you take advantage of, say, gradient modulated STDP. I have no formal definition of what that might mean, but by putting these tools out there, hopefully someone here might be able to make something useful of it. We haven't done anything useful with it yet. As it turns out, the way that PyTorch seems to initialize parameters really sucks for STDP. And so for some reason, I just can't get it to do anything useful. But yeah, we open source these things in the hopes that we offload some of that burden to the community, right? And so, yeah, cool. I started off with hardware, had a slight detour through software during that 2-year lockdown phase in Australia. And with that kind of being done, I started working on open source hardware, right? Google threw a heap of money at Skywater, a Department of Defense foundry, and basically convinced them to open source a 130 nanometer process design kit, and they were underwriting the cost of a bunch of chip tape outs, if you're not already aware of that. Rigid alluded to this in his talk yesterday when he was talking about his asynchronous tools. And so just a really brief summary of what this is capable of. eFabless have created this, what they call a harness, which kind of pre-designs a bunch of pads around your chip. They have Open RAM memory cells on there, 38 programmable IOs. You have a Pico RV32 processor, which I think they've updated in the latest iteration. A few other things. There's a bunch of logic analyzers, so you can program some firmware so that you don't need to keep on, I guess, recreating a bunch of IPs, and you can rely on the things that are already there. You design your core, typically in Verilog. I don't think they have support for system Verilog yet. But then you throw that into your user project area, about 10 square millimeters of die space to play with, and bam, if you're lucky and if you're chosen in the 40 designs that Google will pay for, then I'm pretty sure that choosing process is a complete random process, probably. Then you get a chip. There are a few caveats with that, and I'll get back to that in a moment. So before, oh, awesome, I've got slides that talk about what I just talked about. So yeah, like I said, deep learning was a major success. A lot of people understand it because of open sourcing, right? We can follow code. So let's do the same with what's typically had an incredibly high barrier access and port this over to silicon, over to hardware. Now, before subjecting my grad students through the pain of a tape out, I wanted to see how functional the open source tools were myself. And so I kind of went through the all-nighters and went through the pain, and then I could justify that, if I can do it, then you should be able to do it too. And we've done a couple of designs. You'll notice that these are just GDS2 layout files, so I'll explain why in a moment. But yeah, the first chip in the 6th iteration of the multi-project wafer is sponsored by Google. Just an online event streaming accelerator. You pump it with data we expect from, I guess, like a DVS type camera, so ones and zeros. And then we were able to achieve a clock frequency of 210 megahertz, which was limited by the onboard PLL. The GPIOs had a 50 megahertz peak, but we managed to make those all work together. A couple of neat tricks to speed this up, but don't need to focus too much on that. And then subsequent design led by my grad student Peng, which did a DFF RAM-based accelerator. Didn't go too complex on this. We kept it pretty lightweight and small scale on a shared die with a few other projects. And yeah, managed to get a couple extra little features out there. So following on from that, of course, these are highly, these are binarized SNNs, right? So there's the question of how tolerant to SNNs to quantization and binarization. Turns out, very, very tolerant. Of course, everyone's favorite data set MNIST. So it turns out that when you binarize and approximate a lot of the operators in your spiking neural nets, it turns out that they're a lot more tolerant of these types of approximations and quantization schemes when compared to non-spiking neural networks. My working theory is that this is a result of guess a lot of noise just being absorbed into the sub-threshold dynamics of a neuron. Say you inject it with, I guess, that sort of hardware noise that Kurt was talking about, or with quantization noise. Then as long as it doesn't perturb the state of your neuron enough to trigger or to, I guess, delete a spike, then you're good. Then your network can effectively tolerate it and we have no problems. So that's all well and good. It would be interesting to see how this scales to more complex data sets. I think we're at a point where even DVS gesture has been a little bit done to death, but yeah, open to seeing how that works out in future. Now, following on from that, those were 2 chips on shared dies. This is a tape-in done by Farhad, where he developed OpenSpike, which was just accepted for ISCAS quite recently, which is cool. It was based on Matthew Goothouse's OpenRAM SRAM macros. So yeah, I won't go into too much detail. In this case, this wasn't a shared die, so we had that to play with ourselves. And in a very brief nutshell, in order to reduce the dependence on multipliers and get everything fairly, running very quickly in this particular setup, we have a very constrained approach to, I guess, how the state of neurons are going to be calculated. And so we had a few discrete points at which we permitted the decay rate to be, and we relied on, I guess, right shifts and permutations of right shifts to divide down the membrane potential and various permutations and sum them together. So a couple of interesting tricks to get this thing to speed up. A bunch of other numbers that I'm not too interested in. This is, what is this, 1,000 times worse than your chip, right? So we're at 130 nanometers, but I guess that we weren't too concerned about that. We were just happy that we got something working in the open source tools, right? I should also mention here that Farhad is actually, well, at the time of designing this, he was a second-year undergraduate student. He's still currently in Iran, hoping that he'll kind of make his way over to the States to pursue graduate research. And just in more promotion of the open source movement here, he was designing this while Iran had a lot of protests for women's rights going on, right? And students were getting shot at Sharif University and many of those, I guess, other top tier universities, right? And in our meetings while he's designing this, I could see heartbreak in his eyes. Having access to these tools, and it's a very challenging thing in Iran to get access to those NDAs that let you design at TSMC, not even 5 nanometer, just any nanometer, right? It's kind of depressing, but because of this whole movement, he was basically able to kind of have an escape there and get a paper in the process, which I'm really proud of him. And of course, it's a testament to how much impact the open source movement can have on people that we don't necessarily see right in front of our faces, right? So with that being said, let's kind of close the loop back to RRAM, because that's kind of why I started this in a way. Now, of course, communicating noise-prone signals down a bit line is a bit of a challenge. That's something that we were trying to address by removing all of our data converters. On the other hand, spike-based processing lets us be a little bit more tolerant of all of these non-idealities. So what we're currently working on is an approach that, that does this all fully open source, but say you apply some input voltage on your word line, and because I guess you have a bit line capacitance associated with that, you can integrate charge over time. And one thing that I think is kind of neat is, right, a few of us have alluded to this idea of leveraging non-idealities in RRAM, using noise to perhaps regularize your network, and in this case, using noise to generate a heterogeneous decay rate, because of course, if you have varying RC time constants and you rely on that to discharge a capacitance that's seen on these bit lines, then you can kind of modulate this, this membrane potential decay rate using the natural dynamics of your circuit, which is kind of neat. And for a bit of intuition on why that matters, otherwise, I mean, you can read Dan Goodman's Nature Communications paper on this, as to why heterogeneity matters with membrane potential decays. But as a little bit of intuition from the DVS gesture data set, you've kind of got this fulcrum point at the elbow, which isn't changing very much. So in a way, you don't need long-term memory for these events. Whereas with your fingertips, that's something valuable. Having longer-term memory to remember that an event triggered is important. So these are features that vary on different timescales, and that's something that can be exploited by using RAM that has variation, or that can be programmed to a varying degree of values. And yeah, given that these are spikes, remove your data converters, so happy days. Now, I'm pushing for open source, right? And I'm very glad that for all of big tech's flaws, one thing that I'm very pleased about is that Google threw enough money at Skywater to have them release. This was just in August 21. So they threw enough money at them to convince them to release the, I guess, Sky 130B PDK, which includes RAM in the back end of the line. So effectively, it's one pretty neat way to be able to tape out RAM chips for free, right? A little bit of info on the process. It's a hafnium oxide-based RAM with 0.1 to 0.2 voltage readouts, with various set voltages and reset voltages and substantially higher forming voltages. So yeah, we face a few challenges here, right? It means we might need charge pumps to be able to get access to all of these voltages. You need reasonably larger select transistors if you're going for an active array, because you need to be able to sustain the current that comes from those forming voltages. And so that hurts density a little bit, but it is what it is. That's kind of what we want to address. Like, the RAM is a pain to deal with, but by offloading some of that burden to the open source community, then hopefully we'd be able to come up with ways to get around that or work with the constraints that we have. Another issue is that timing errors are a pain. So one reason that you haven't seen any actual dies from the open source chips that we've worked on is because we haven't received them yet. Some of the tape outs have taken over a year or so, and that's because the harness that I showed you earlier had some top-level timing errors that were, I guess, not correctly configured for the core that you designed. And so while eFabless and ChipIgnite and some of the third-party people in that overall process are figuring those out, we're kind of left wondering where our chips are. So you get what you pay for, which is, in this case, $0, which is awesome. But there are people that are spending $10,000 to get guaranteed slots on these wafers. And so for them, I could understand their pains here. So yeah, a few pain points. But yeah, it is a start. And I bring this all up because of expectation management, right? It is a very cool initiative that all of these little pieces, from your tools to your process design kits to the tape out process itself, have been open sourced, but can't get everything yet. Hopefully that will be fixed soon. So can we move Thomas away from the edge? When I say edge, I don't mean this cliff. I'm saying in the spirit of, I guess, what Christian was saying yesterday, where neuromorphic is, a lot of people are talking about it operating at the edge, but if you get low power in lightweight systems, then doesn't that transfer to low power in large weight systems? So heavyweight systems. So obviously I have to talk about this. So Spike GPT, one of my grad students, Regia, pretty much put this all together over the course of a very, very sleepless month. We put out 3 variants, and they're currently hosted on Hugging Face. So 145 million, 120 mil, and 260 mil parameter models. I think, and feel free to fact check me on this, but I believe that it's 4 to 5 times larger, or 260 million is 4 to 5 times larger than the, I guess, largest scale SNN trained via surrogate gradient descent techniques. Yeah, we've faced a lot of challenges in keeping up with the deep learning folk, and the vanishing gradient problem just gets a lot more difficult when you constrain your activations to 1s and 0s. A couple of performance samples, again, for expectation management reasons, but I'm not sure if you can read this, but in the case of the 120 million parameter model, gave it a start token and said, tell me what you feel like saying. And in this case, so it starts giving me this poetic, well, it is trained on the book corpus data set, so fair enough that it wants to tell me a story. What does Spike GPT say? I looked up at him, the corners of his lips pressed together. I don't know. He looked at me and I was staring at him. Very, very, very beautiful, right? No, so it is kind of, it's syntactically sound, but semantically pretty weird. But if you saw this a year or 2 ago, you'd probably be very impressed. Pre-ChatGPT days, right? The 260 million parameter model, we were able to give it some more domain-specific tuning using a bit of context and leverage a bit of Q&A. Do I need to shut up soon? Yeah.
Well, we are running out of time a little bit.
All right, I'll shut up
in like give you a minute to wrap up.
A minute. All right, I'll start wrapping. Cool, 260 million parameter model. So all well and good. It's based on a recurrent variant. So feel free to talk to me about that in person. Far fewer synaptic operations for what it's worth. Of course, synaptic reuse is what tends to matter when it comes to actual hardware implementation. But yeah, there are some caveats to this. All of our matrix vector multiplications use spike-based activations. Our element-wise operations, such as your Hadamard products and that, use full precision. It's kind of akin to membrane potential decay. Some other stuff that we've done includes temporal feedback learning. In the interest of time, come talk to me in person if you're more interested about that. But we did some other cool stuff there. And I'll give a plug to some upcoming opportunities for Neuromorphs. But if you want to get involved with open source hardware, of course, you're more than welcome to Google things. But we're also sponsoring the Tiny Neuromorphic Tape Out project at the upcoming Telluride workshop as part of the open source neuromorphic systems topic area. But the goal is to basically get anyone that can't or doesn't know how to design a chip to be able to design a chip in the space of 2 hours, going from 0 to basically ASIC. You do have a very small constrained amount of chip area, and I'm trying to see if we can make this remote. And we've got 250 slots. I think the first 50 will be completely free for people to design with. Everything after that, there might be a $25 fee so that we don't go broke. But yeah, of course, it's slow because we use a scan chain to connect all the designs together. Yeah, I think that it would be very cool to get as many heterogeneous designs on board, and you'd be able to play with other people's designs as well once you've built your own thing. So you don't need Verilog skills. You could do it schematically using Walkwe. But yeah, it would be awesome to see a few of your designs on this. So with that being said, I'd like to thank all the students that have kind of worked on this with me, and that's what I've got to say.